Okay, in the previous video, we figured out what the acceleration would be for a solid disc rolling down an incline if it was not slipping. So let's take that and go one step further and figure out what's going to be the force of friction. And remember that this is static friction. So the force of static friction can only go up to a maximum value. So at some point, if the surface is slippery enough or if it gets steep enough, then the force of static friction is not going to be able to be big enough to cause the torque needed to supply this angular acceleration. And in that case, it will start to slip instead of rolling without slipping. So let's first see what is the force of friction, and then we'll figure out under what conditions would it start to slip. So let's get rid of some of this information that we used to solve for the acceleration, and then we'll just keep the information about the final answer for the acceleration. Okay, so now that we got all that other stuff out of the way, let's focus on our new problem. So our new problem is going to be to find FFS. Now, maybe I shouldn't have erased all those equations because we did have an equation already that had FFS in it. When we solved for the torque equation, we wound up with FFS is equal to 1/2 times m times a. And then that's what we plugged back into the Newton's second law equation to solve for the acceleration. Well, now that we found the acceleration, we can go back to that equation. Remember, this just came from the torque equation, and we can plug this in for A. So this is all we have to do to figure out the force of static friction. Force of static friction equals 1/2 times m times 2/3 of g sine theta. So the force of static friction, if we simplify, is going to be 1/2 times 2/3. That gives us 2/6, which is 1/3. 1/2 of 2/3 is 1/3, I suppose. So 1/3 of mg sine theta. And m was a given, g is a constant, and theta was given. So that's our answer. So this is the actual size of the friction force. So you might notice that this component is mg sine theta. And so what this is telling us is that for this case of a solid disc rolling down an incline, the actual size of the friction force is going to be 1/3 of the x component of gravity. And that makes sense that it's going to accelerate in this direction then, because this force that's pulling it down the incline is going to be larger than this force that's pulling it up the incline. Now the second question is, what is going to cause this to slip? Because it's not necessarily going to roll without slipping. So actually, to answer that question, we need to add one more piece of given information, which is how slippery is the surface. So that's going to be the coefficient of friction. So if we're just interested in the point at which it begins to slip, we need to know the coefficient of static friction. So if you think back to your friction days, one thing that we know about static friction is that the force of static friction is less than or equal to the coefficient of static friction times the normal force. So what we want to know is what's the maximum possible value that the static friction force can be before it'll start to slide. So if we want to know the FFS maximum, that would be when it's equal to the coefficient times the normal force. So our maximum possible static friction force in this case is going to be mu s times this normal force. Now the normal force has to be equal and opposite to this y component of gravity. And that's because there's no other forces pointing in that direction. And so those have to cancel each other out. So this y component of gravity, that's going to be mg cosine theta. So that means that the normal force also is going to be equal to mg cosine theta, just pointing in the opposite direction. So down here for the normal force, we can fill in mg cosine theta. So that's the maximum that the static friction force can be. So if we want to figure out what the maximum, at what point this is going to slip, then we need to relate this to the actual force of static friction. So this will slip when the actual force of static friction necessary to keep it rolling reaches its maximum value. So what we want to do is plug in this expression for the maximum force of static friction in for the actual force of static friction. So let's see what happens when the actual force of static friction reaches its maximum value. So if we plug that in, then we get mu s times m times g times cosine theta, that's our maximum static friction force, is equal to 1/3 mg sine theta. And so the m's can cancel out because there's one on each side. The g's can cancel out because there's one on each side. And then we may want to write this in terms of tangent theta. So if we put both of the theta terms on the same side, say we divide by cosine theta, then we have mu s equals 1/3 of sine theta over cosine theta, which works out to be tangent theta. So it's 1/3 tangent theta. So sine theta over cosine theta is equivalent to tangent of theta. So this is going to start to slide when theta is equal to 3 mu s, and then the inverse tangent of that. So if we had if we knew what the coefficient of friction is, then that would tell us the maximum angle that we could tilt it before it's going to start to slip while it's sliding. Also, we could go the other way, and we could say if we have a set angle, we can figure out what the minimum value is for the coefficient of friction. What is the minimum amount of stickiness or roughness that we need on the surface in order to cause it to roll and not slide. So this is our final statement. A little messy, but that's okay.